All right, so these are referred to as our addition and subtraction formulas for sine and cosine. And then obviously we have our tangent. And this is kind of what I was talking about earlier is, if I learn essentially this one and that one, they will give me that one through the use of our identities. Because tangent is sine divided by cosine, right? So if I take sine of s plus t divided by cosine of s plus t, that should give me tangent of s plus t, which through then looking at that side divided by that side, and we'll do this proof, but those two sides divided by one another should evaluate to give me that. Okay. So by knowing, if I think about it, if I just focus on learning those four, it should provide me ultimately those two. Okay. But if you look at how these two are very similar, and these two are very similar, ultimately they're the same except for those signs, right? Okay, those are differing here. And what you may see in some textbooks, I wish this one would have done this, but you might see it written this way, where it goes sine of s, and then it will put a plus and a minus, and then t, and then we'll write this as sine of s cosine of t. Now this top one is a plus, so the top one here I'm going to write is a plus. Okay, the bottom one is a minus, so the bottom one is going to be a minus. Does that make sense, everybody? And then cosine s sine t. So that means if I use this top sign here in this identity, or this formula, I'm going to use this top sign over here. Does that make sense? If I use the bottom one, I'll use the bottom one. That's different for cosine, because cosine, it'll go s, again, plus or minus t, but now that should equate to cosine s cosine t. But now you see that if I use a plus, this becomes a minus, right? So the top one here is going to be minus, and the bottom one's a plus. Okay? So you see, if you use a plus over here, it's a minus, and then you go sine s sine t. Okay? If you use the minus over here, it becomes an addition of these terms over here. So sometimes you'll see them written as those red formulas. I want to show you what this is, what the purpose of this is. If I have, and we'll just deal with cosine of s plus t and maybe sine of s plus t for now. Cosine of s plus t. We just said cosine of s plus t was cosine of s cosine of t. And then it became minus sine of s sine of t. Okay? And sine of s plus t was sine of s cosine of t cosine of s sine of t. Okay? Something that's going to help you as you go through these, you notice that the objects, st, 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 they're in that pattern that you see right here, right? S first, and then t. So st, 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 st. It's kind of always the pattern with all these formulas, okay? So it's never like cosine s, sine t. It's st, st, okay? So why is this useful? Okay, or how is this useful? We are going to be interested in maybe asking what is the exact value of cosine of maybe 75. 75, and we'll do this in degrees, so 75 degrees. We don't know that from the unit circle, do we? Nope. But we do know this, that 75 is the same thing as 30 plus 45, isn't it? And if I know cosine of 30 and cosine of 45, along with the sine of 30 and sine of 45, I should be able to use these two red formulas to evaluate this. That is ultimately your S, and that is ultimately your T. So I want to rewrite this thing here now. So it's cosine of s plus t becomes cosine of s. So it's going to be s is 30 times cosine of t. T is 45. Minus then sine of s. So that's 30. Sine of t, 45. And you see that if I'm interested in cosine of 75, these formulas break that 75 apart into two values that we know how to deal with. What is the cosine of 30 off the unit circle? Radical 3 or 2, isn't it? What's the cosine of 45? Radical 2 or 2. I know some of you have forgotten these. Okay? You cannot forget these. These are, we're going to continue throughout the, it's been a while since we actually evaluate off the unit circle, right? Maybe been a week and a half. And that's going to be the practice. We'll use it for a week. We'll take 3 or 4 days off of it. And we'll come back and see an example that uses it. And we'll take a week off. And we'll come back and use an example that uses it. Okay? So you cannot forget these. Okay? Sine of 30 is 1/2. Sine of 45, radical 2 over 2. You can do that multiplication. That gives you radical 6 over 4 minus radical 2 over 4. So that's actually root 6 minus root 2 all over 4. So, and you're not going to memorize these guys. That's why we've got the formulas. But we now have the x-coordinate on the unit circle for 75 degrees. Okay? And it's that thing right there. A lot uglier than any other x-coordinates on the unit circle, right? Okay? But that is the exact value. Now, we should be able to do a similar thing with the sine. So we do sine of 75. Well, that is going to be broken up as the sine of 30 plus 45. So sine is going to be sine, cosine. We use the same sign that's there. And cosine, sine. Okay, so it's just fitting back into that thing there with s and t being 30 and 45. And again, we evaluate. We know sine of 30 is 1/2. We know cosine of 45, radical 2 over 2. Cosine of 30, radical 3 over 2. Cosine of 45, radical 2 over 2. And you can write that however, it's commutative property, so you can write it as radical 2 plus radical 6 or radical 6 plus radical 2. All right, so what does that mean to us? If I look at the unit circle, okay, here's the unit circle, and I've changed this arc to 75 degrees, okay, or this central angle to 75 degrees, how you feel of looking at it. And now that ordered pair right there, where my cursor is found by radical 6 minus radical 2 over 4, comma radical 2 plus radical 6 over 4. Okay? If we use Desmos to prove this to us, okay, I've typed in cosine of 75, and it gives me this number right there, right? Okay? The cosine is actually, it was the, was it radical 6 minus radical? Yeah. Do you agree that cosine 75, that number right there, and that number right there are the same? Okay? And if I do sine of 75, well, that turns this into addition. Would you agree that sine of 75 is exactly the same thing as that number there? Okay. So these formulas are doing the exact same thing that our 30, 60, 90 triangles did for us when we developed these other unit circle values. Okay? They're finding the exact location in our XY plane of that point on the circle. I should be able to square this, square that, add them together, and get what? What's cosine squared plus sine squared always going to equal 1? Okay? So those 2 points together satisfy the unit circle. Okay? What I want to do right now, and we'll see more examples, we'll do more of that tomorrow. I want to prove this with you. Okay, so it's going to take, now we might go through this quickly, and I might have to kind of extend the video into Wildcats on, but I want to see as far as we can get proving this, because it is going to kind of practice our algebra skills and practice our identities. We see a lot of identities here showing up. First thing is we're going to create a unit circle, and we're going to put these 4 points on it. Okay, this point needs to be as 1, 0, and these other points can ultimately be anywhere they want to be. Okay, it doesn't really matter. But I want to come up with what the coordinates of these points are. Obviously, we've already got this one pretty easily. I want to look at an arc, that blue arc. I'm going to call that blue arc T. Okay? If that blue arc is T, and we're all in the unit circle, isn't that point Q1 determined by that T? So for instance, if T was like pi over 6, wouldn't this be cosine of whatever pi over 6 is? Comma sine of pi over 6, right? Well, I don't know it's pi over 6. All I know is it's T. So I'm gonna identify this point as cosine T, sine T. Is that fair? I'm going to find this arc here, this red arc. We'll call that red arc S. And now this point up here, it's the same idea. If I'm looking at, whether it be the arc or the central angle, isn't that angle S plus T? Or the arc S plus T? Does that make sense? So shouldn't this be, for the same reason this one was, a cosine of the arc, and the arc is S plus T, comma the sine of that arc, which the arc is S plus T. Is everybody all right with that? We can do arc addition. Now I'm going to take another arc. I'm going to start at P sub 0, and the other arc is going to go in the other direction. But I made that one red, because I want it to be the same length as this one. But if it's going in that direction, should I call it negative S? That's what that arc would be. So this point down here would be cosine of negative S, comma, sine of negative S. Correct? Okay. Now, do we like negative angles? No. We don't like those arguments being negative. So we're going to use our even and odd identities, if you remember them. Cosine of negative S was exactly the same thing as cosine of S. Okay? Would you agree that if I take this red arc and then put another one up here, that the cosine of maybe that point there and the cosine of that point right there would be the same thing? So that's what the even and odd identities are saying. So I'm going to rewrite this point actually as cosine of S. And we also had this identity, sine of negative S, is the same as the opposite of sine of S. So I'm going to rewrite this y coordinate as that. And I'm not interested in using that one. Is that doable? That's just the structure of the points that we want on the unit circle. Now, every arc on the unit circle is subtended, okay, subtended by one of those things. You guys know what one of those things is called from geometry? Segment that intersects 2 points on a circle? That's a chord, okay? And the arc that is subtended, or intercepted, created, maybe there's another word, but subtended is the geometry word that we see. That arc would be s plus t, wouldn't it? Okay. What about this chord? What is the arc of that chord? It's still s plus t, isn't it? The negative is just telling me a direction for that arc. Does that make sense? So that length is still s plus t. So those two arcs are the same length, right? What's that tell you about your chords? You remember from geometry? In geometry, we had a theorem that said two chords that subtend the same or congruent arcs are congruent. Okay? So these dotted lines, they're the same. So could I say, now one dotted line we say is P1, P0. The other one is Q1, Q0, right? Those distances should be the same. Do we have the ability in the coordinate plane to use the distance formula? You remember the distance formula is this thing, right? Distance is equal to x2 minus x1 squared plus y2 minus y1 squared. Remember that? Okay. Let's just deal with P0 to P1. That's the easier one right now. Okay. And I'm going to, oh, it's going to get ugly. The size of this thing is just eating up a lot of my room. Let's say P1 to P0 is equal to the square root, okay? I'm going to take this x minus that x. So it would be cosine of s plus t minus 1 squared. That is the difference in my x's squared. I'm going to do the same thing with my y's. So it would be this y minus that y. So that just becomes sine of s plus t, and we'll square that. Is that okay? So that is the distance of that chord. Can we do the same thing with the other chord? Okay. So we'll have Q1, Q0. That is going to be equal to the square root. Okay. We'll take this x value minus that x value. So I have cosine of s minus cosine, I guess I did that backwards. Cosine, it doesn't matter, but do it the way I said. Cosine t minus cosine s. We'll square that. We'll then add to it the y value subtracted. So sine of t. Now minus a negative becomes positive. So plus what am I? Oh, yeah, I don't know what I was thinking. Sine of s squared. Okay. That minus that. Okay. Is that doable? All right. So now that we have that, I don't care about the picture anymore. So get rid of it. We have these two distances. And these two distances should be what to one another? They're congruent, okay? Now, they're both under radicals, right? So if they're both under radicals, I could square both sides if I want to, right? Would that get the radicals go away? Okay, so I'm going to have, and we're going to go through this pretty quickly because we're going to run out of time here. I'm going to have cosine of s plus t minus 1 squared plus sine of s plus t squared equal to cosine of t minus cosine of s squared plus sine of t plus sine of s squared. Okay, that's the inside of the red radical. This is the inside of the blue one, right? Now we've got a bunch of binomials squared here. So I'm just going to go ahead and evaluate this. Okay, I'm going to FOIL this binomial, so it becomes cosine squared of s plus t minus then 2 cosine of s plus t plus 1. I'm going to square this, so it becomes plus sine squared of S plus T. I'm going to FOIL that. Cosine squared T minus 2 cosine T cosine S plus cosine squared T. And we'll FOIL that. So it becomes sine squared T plus 2 cosine T, sine T, sine T, sine S, and then plus sine squared T. Okay, so a lot of garbage there, but we'll get through it. What is, we'll go through it and substitute here. What is that plus that? 1. So then the left-hand side turn into negative 2 cosine S plus T plus 2. Okay. What is cosine T plus sine T? 1. Okay. What is that one plus that one? 1, right? So do I have a 2 over here? Minus 2 cosine T cosine S plus then 2 sine T sine S, right? What are these twos going to do? Cancel each other out. Additive inverses, right? What does every term now have in it? Yeah, they all have a negative 2 in them, right? Can I factor a negative 2 out or divide a negative 2 out of everything? So when I do that, it gives me cosine S plus T. Divide this by a negative 2, gives me cosine of T times cosine of S. Divide this by a negative 2, gives me a minus sine of T sine of S. Now, usually we see it written this way, S plus T. Can I use the commutative property of multiplication to flip-flop those? All right, and that becomes the proof of that formula. I think it's a good idea to eventually go back and watch that video again of how to create that. Thank you.